All right, today, ladies and gentlemen, let's begin. We're gonna start our discussion about rates of change today a little bit, this will be hopefully this picture will become obvious why we're picturing it this way, even in the next couple minutes. Ms. Getz is representing some kind of curve, of some kind. Maybe it looks like some kind of a cubic or something. Who knows? And both Mr. Davis and I are illustrating tangent lines to the curve, and we'll talk about why that might be something that's interesting to us later. Again, with the pool noodles, you gotta get the pool noodles in the picture. Okay. So we're gonna open with like a really kind of basic question that you might even ask in an Algebra 1 class, and that's, what would your average speed be on my trip to New York City over the 5 hours that it took me? I guess I don't know where we're starting from necessarily, but imagine it took you 5 hours. And it looks like, just go with the picture here too, it looks like maybe it was 300 miles away. So is that here? I feel like we're close. I feel like we're closer than that, but maybe. Is it about that? Yeah. Okay. All right. We'll go with it though. Say it's exactly 300 miles away. We don't know the function here, but please don't think too hard. What's my average speed? Anybody? 60. I hear some people say, and how is the calculation done? Of course. Yeah, you are basically, you're thinking, okay, 300 miles is how far I traveled, and that was the total distance divided by my time interval, which was 5 hours. It's also, why have I drawn this blue, it's hard to see, I apologize, but why have I drawn that blue dashed line? How can we think of the thing you just calculated, isn't it? Okay, true, yes, and that's what I asked you to calculate. It's not necessarily the line of best fit. I actually connected the point at the bottom and the top. The line of best fit doesn't necessarily have to go through those. What'd you say? Yeah, it's the slope of that blue dashed line, isn't it? Take a second to digest that, of course. What about your average speed on the interval 3.5 to 4? Now, clearly, I didn't provide any information enough to calculate that. But how would you? How would you set it up if you had access to f of x, if this is some function? You could evaluate it wherever you like. If you needed to, how would you do it? Just name the process. I we can't come up with an answer here. But, Rebecca, go ahead. Find the slope. So how would you do it? Actually say what the calculation is.
Oh, okay. So you take the y value of 4 minus the y value of 3 over
3.5.
Oh, 3.5
Cool.
over 4 minus 3.
3.5. Yeah. Great. Exactly. It's that little tiny line segment I just drew there. Right. The slope of that line segment. Yes. Good. I'll just extend the line segment out so you can see it just a little better. But we could find the slope of that line segment, and it's exactly what Rebecca just said, isn't it? It's just the way you calculated Algebra 1, isn't it? The difference in the y's over the differences in the x's. And I'm using this notation to say this is the slope of, in subscript I have SEC as in the secant line. So I don't know if you remember this in geometry, but we'll broaden the definition of a secant line now, but like when you're looking at a circle, you would call a line like this that cut the circle in two places a secant line. So that should ring a bell a little bit. Okay. So, moving smartly along. What about our average speed? Oops, sorry. I have some things happening here. Yeah, let's call this interval h here. This distance between x2 and x1, h. So we'll make that replacement. Then really all we're talking about is one particular value of x, and we're letting h be a distance away from x. So in this case, h is what? 0.5, right? Isn't that like the distance between the two? And this means exactly the same thing that we just did. Would you agree that like x is 3.5 and h is 0.5, then what we've done is we've kind of quantified that. We've just really just rearranged the symbols, not much more. And then my question would be like, what about our speed at x equals 4? And of course, that you might be thinking, how do we calculate the slope at x equals 4? Is that possible, or is it even meaningful? And the answer is, of course it's meaningful, because if you were in the car when it happened, you could have looked down at hour 4 on your stopwatch, and you could have looked at the speedometer and been like, yes, we are traveling at exactly, well, who knows what it is, I don't know how fast you were going at that moment. But of course it makes sense to me that that would be a question we're allowed to ask, yeah? I think you agree with that at least. So how do we conceptualize that? How would you find that if you could? Again, if you had access to this actual function, if you had a little more information or a better picture. Yeah, what are we trying to, what was your, a really good approximation right now?
How does your distance go down? Or the distance would be?
It shouldn't. Yeah. Maybe you took a, yeah, maybe you're taking a clover leaf and you came toward your, sorry, I don't know. It isn't meant to be non-decreasing anywhere, you're right. It's almost right, right? What was my question? Oh yeah, how do we calculate the instantaneous speed at x equals 4? How would you do that? Or, here's another question. How do they calculate with radar your speed? Do you know how either the cameras or the cops with a radar gun do it? They don't actually calculate your instantaneous speed. I'll just tell you that. They don't do that. Yeah, they ping you twice, right? They take 2 measurements, and what's good about those 2 measurements? What's important about those 2 measurements? That they're really, really close together, right? And they get an approximately good estimate for your instantaneous speed at that time, right? And that's the idea here too. And if that's the desire, then what do we want to happen to h? Well, we'd like h to be really small. We'd like it to be as close to 0 as possible, wouldn't we? In fact, we have a notion to capture that now, don't we? We'd like to limit as h goes to 0 of this expression, right? And what that gives us is at that any given point that we're interested in, it gives us the slope of a tangent line, which is the way to picture, for us, the instantaneous rate of change on a function. It's just the slope formula from algebra 1. Just take the difference to 0. That's all. That's all. There are different ways to conceptualize this, right? The other way you could use the original formula we had to have x2 approach x1, right? The limit as x2 goes to x1. There are a couple different ways to say this, but the principle is the same. The big overarching principle is the same. Slope of the tangent. Let the difference in x become infinitesimal. And then we get, does that fit? I don't know.
Go back.
Then we get a nice tangent line to the curve, and we can calculate its slope. That's kind of a big idea, that we can maybe find the slope of a curve at a point when it's not a line. I mean, I understand what the slope of a line is. That makes sense. But of course, now we can conceptualize it in any curve at all, even this crazy one here. So just to recap again, we have 2 notions right now in play. We have the average rate of change, which I also want you to think of and equate with the slope of the secant between 2 points, and with the instantaneous rate of change, which I want you to think of when you visualize it as the slope of a tangent. And it's the same formula with a limit stuck in front of it, right? Okay. So just to, I know we said that on the last slide, but I just want to just really highlight that. Notice, of course, that this is a limit. And so when do we have an instantaneous rate of change? It's defined, well, exactly when the limit is defined. If the limit fails to exist, then the rate of change at that point fails to exist. It's just a limit. Why are those hands there? Pull this out with the cute graphics. Looks like 2 hands. What? You gotta interpret. I stole that from Ms. Getz. I could interpret Ms. Getz's graphics. know this is a left hand and the right hand, and you're supposed to think about whether the left and right hand, what exists, right? What the match.
Oh.
I think that's what that's supposed to evoke in our minds. I think so. Okay. Give a holler. Just let me say. Holler. Here. Homework. One on here as well. All right, let's take a look at a function as an example. Again, we're going to look at this function f of x equals 2 plus cosine x on the interval 0 to pi, and the average rate of change is what we seek over that interval. Remember, by average rate of change, we also mean the slope of the secant. So we'll think about this in terms of just like our algebra 1 formula, right? Just the difference in the y's divided by the differences in the x. So on this one, actually, I think we can, I won't put up the answer yet here. I think we can evaluate those without a calculator even, yeah? So plug in pi, plug in 0. What do you get? 2 plus cosine pi is 1. And then 2 plus cosine 0 is 3. So what are you getting? What do you get? What do you get? So you get 1 minus 3 over pi minus 0. So I think for the slope of the secant, we get that. Someone could easily ask you also for other things. By the way, here's the picture, right? Does look like it should be a negative slope, so that's good. Someone could ask you for other things too, like could you come up with the equation of that blue line? And the answer is yes, of course I could. That's another algebra 1 task, isn't it? I have the slope of that blue line now, don't I? And would you like a point? Let's be lazy. How about this one, right? Or this one, doesn't matter. I guess here I have this one chosen, but this would be the easier one, right? I don't know, whatever. Anyway, I'm using, like I told you, I think I promised even the first week that one of our favorite forms of the equation of the line will be point slope form, because we're often going to be in this situation. Here we are in this situation. We have a slope and a point. It just will happen a lot, because the slope is a lot of the conversation we have in calculus. Now here we actually do have the y-intercept. So you could write it a couple different ways, but obviously we expect you to be able to do that. Anything else you want to say there? You're dying to calculate the slope of a tangent line, though, aren't you? Let it begin, let it begin, I hear you say. Well, you have to wait one more slide, sorry. Just a one little pause here. I wanted to say one thing about units, just real quickly. In this picture, this looks like maybe the parabola x squared plus 2 or something. If I'd like to find the average rate of change on 0 to 2, obviously it's the change in y over the change in x, it's the slope of the secant, it's all the things you rise over run, however you want to say it. Imagine, if you will, and it's 2 here, that's not the point of this. Imagine, if you will, though, that y is being measured in feet and x was measured in time, and maybe this is a dt graph or something, right? Then what are the units here associated with this answer? Is it clear that what we're doing here, what is this measured in? What is this measured in? Yeah, it should make sense that as our answer we get something in feet per second. Now that makes good sense in this context because we think of rate of change, we think of distance and time, we think of velocity, we think of speed maybe or whatever. Wonderful. Other times it might be less apparent, you know, like it might be like bushels of apples per pounds of fertilizer or something, right? It could be all sorts of other more exotic units. So, but in general, that's always going to be what we do. We divide units in y divided by units in x. And that will always work even in strange situations. All right, so now actually, like, let's think about the slope of the curve at a point, the instantaneous rate of change, the slope of the tangent line of a parabola at x equals 2. So we're going to use, here's the picture. There's the point if you want it. We're going to use this limit definition. Okay. So the limit, I'm going to do it over here, as h goes to 0 of f of, in this case, we have 2 plus h minus f of 2 over h. And in our case, f we know, it's x squared plus 1. So what do we get? 2 plus h squared plus 1. Do you agree that that's f of 2 plus h in our case? Minus f of 2, which is, well, I could write it here. It's 2 squared plus 1, but we also have, we already calculated it's on the board. Over 5 minus 5 all over h. So far, so good. Let's keep rolling. And now our task is really just to do the things we've just been doing, even on the AP problem just now. Can we evaluate this limit? When we do, we'll be done, right? It'll be pretty exhilarating. Okay. Good. 4 plus 4h plus h squared plus 1 minus 5. What's going on upstairs? Anything you see? Convenient, right? What do you see? Yeah, the 4 and the negative 4 cancel out. So we just have 4h plus h squared over h. And then what would you like to do? By the way, the whole goal our entire time, since the very, very first line of this, the very first thing I wrote, is I'd love to evaluate this when h is 0, right? But I can't yet until right now, right? And what do I get as my answer? If h is 0, I can plug that in. I get 4 as the slope there. Now, one thing you can do too, and we do need to find a stopping point here because the bell's going to ring in a second. But so we'll pick up here tomorrow. I don't know how much we'll be able to cover. I don't know how much of the homework you'll be able to do, homework 1, but you should be able to do some of it. But my thought would be, what would happen if we just kept the x in there too? We'll discuss that a little bit more tomorrow. Yeah, if you could start homework 1, maybe I won't check it tomorrow for sure, but you should be able to. We'll have time to clean this up tomorrow. I just wanted to get started. Have a great day, everybody. Bye, everybody. Have a good day. I didn't check it today.
I'll show you how the bus. Yeah. Wait. Okay. So then they were like 2 hours late. I'm like, yeah, exactly. Why do you lie about it? It was like Tisha's idea. I don't know. Like, I